All right, so as a continuation of the NEC discussion, the real heart of what we want to talk about with NEC is how do you translate that into mounting fuses in the organ, and how many do you need, and how do you set up a system, and then more on calculations, and I guess we're going to talk about what we do, just to give some examples.
And that's all I'm talking about is what we do. Yeah. It's not saying this is what you have to do.
Yeah.
But that's...
So this is Peter Geise, and Aaron Garbowski is going to participate in this, right?
So like I said, this is... What we're talking about is basically how we have worked with the code and how we have taken this information and applied it in our own instruments. I have a few pictures here of the instrument we just, and it's not completely done yet, but we've been working on it, Holy Trinity Church in Buffalo, New York, and Holy Trinity Lutheran. This organ is 152 ranks. We just rebuilt the main organ, which was 86 ranks, And so this is the power supply bank. It's an electric slider organ. So you'll notice we have 5 75 amp power supplies. So, where are we going here?
Peter, do you have any trouble with the circuit breakers on these power supplies?
No, not at all.
No.
That's something we have had an issue with, so we've been asking the church to replace the circuit breakers with the high magnetic that we talked about this morning.
You have one breaker per power supply?
Yes. Yeah, and this is set up, and should be in the next picture.
Those are breakered at what, 15 amps? Almost
20.
even 20 they're blowing.
Yeah.
These have the 20 amp plugs on them, don't they?
Yes. Yeah, because they are 75 amps. So, and it seems to happen when you turn the organ on. So it's the inrush that seems to be causing the issue.
Yeah.
And of course, this is going to do funny things for me. But
Well, and the problem was, after talking to Bob, what did you say the inrush current is on one of these?
The inrush current can be as high as 40 on those 75s, and full load it's 17 and change.
So a regular 20 amp breaker was just calling it too close.
yeah. So then this is the fusing panel. Because of how we build our slider chest, we have a pull-down magnet and we have 2 smaller relief DE magnets. And so there's a lot of current to play a single note, and so we have a lot of fuses. And we also, in this organ, we have fuses for the slider cards. Those are fused at 15 amps. So it's just quite a large panel with all the fuses. So that was just what I wanted to go through there. And so kind of continuing on that idea, I just passed out a sheet of paper that has how we kind of come up with how many power supplies. You know, Bob talked about this, Dick talked about this. This is how I've done it. So you'll see in this magnet current consumption chart where you've got in the console, you list off how many Harris decays or Syndyne decays you have, and then up at the top there's a box that shows what is what voltage are you operating at, because of course what voltage you are operating at is going to determine what the current you're going to draw. So this the spreadsheet calculates based on the current of each of those how many amps that would draw. And so you can see at the bottom that and this is for the organ you'll see tonight at Canandaigua United Church. We said 155 amp power supply because total current is 36 3/4 amps, And so even with some headroom, 55 is a good number for that. So then if you look at the chamber, and we have two separate chambers, and they have separate power supplies because they have separate control system output panels, which are connected with fiber optics. So there's no voltage connecting between the two chambers, and so we have separate power supply in each chamber. Now, the anyway, you can see at the bottom of the sheet, though, that if I have some assumptions. So under chest magnets, if on main chest, our slider chest, we assume that we're going to play 24 notes at one time. I didn't say 30, I said 24. And I said to add 4 if you've got a pull-down chest, because in a lot of our pull-down chests we have double pallets in the bass, so you're going to add 4 notes. Unit stops, assume 30 notes at one time. Direct valve actions, which would be wicks, you can call it direct electric. Assume 8 of them are going to be 1.25 because the different size direct electric actions, a lot of them have different resistances. We use different coil resistances to get enough power for a larger valve. And then in this organ in Canandaigua, we also did use hoist magnets. They're direct pallet magnets. So we have an assumption for 8 of those have 35 ohm coils for the larger discs, and 22 out of the 30 would be the 58 ohm coils. And so then also adding in relief magnets, which we use Peterson. Did that just move on its own? Anyway. You have the relief magnets, we use Peterson for those. So that's how we calculated power supplies. Now you notice on the sheet, we said total current for the Great Choir Chamber was 145.55 amps. If you add margin, that's definitely over 275s. But because we assume that it's unlikely that you're going to be playing a max out chord while pushing a piston, we did leave some leeway there for that. So, and then in the swell chamber, it's a little bit more straightforward. There's not as many actions to deal with. Questions?
Also, you've got some possible headroom in the current for the slider motors.
Right.
Because they're not all going to be cranked up full.
Right. Yep. That's a good point. And in this spreadsheet, I also separated out chamber voltage and complement, so you can have different voltages, and all of that then is calculated for you. So I like Excel, in case anyone didn't notice. But it especially when you're doing calculations like this, where you're going to be doing the same thing over and over again, it's a good way to do it. And obviously, Bob pointed out there's calculators that would do this kind of stuff for you online. But because we're using the same magnets every time, it's easier to just say I'm going to use this many of them. So that's just. So now if we look at the other spreadsheet, flip the page. So the former sheet was how many power supplies do I need? How much brute power do I actually need? We have in our shop used the standard, as Bob said, we disagree on how are you going to fuse this? Because we assume that there will be someone who will play every note on the keyboard. There's pieces that are actually written that way. We call it the Ligeti effect. So Ligeti's volumina, where you actually lay on the keyboard with all the stops on. So we do allow for that, and because we're mostly doing electric slider, we do have that headroom. You're not usually changing stops while you're leaning on the keyboard. So we do fuse so that you don't have as much of an issue with, you won't blow the main fuse, or you won't blow all the fuses when you lay on the keyboard. You might blow the main fuse, but you won't blow all the individual fuses. So then this spreadsheet does a couple different things at once. You know, based on toe hole size, which is based on scale of the pipe, we know how many sizes of action we need for every stop, and then so we know then how many magnets there are, and then this tells us how many amps. I have in this spreadsheet, there's a lot of hidden rows here, and what that does there's basically a chart saying, okay, for a hoist magnet of all these sizes, this is the resistance we can count on. And then over here, there's another set of hidden cells, which shows you, which goes through the calculation for each size. It tells you, and this is actually called data. Let me just delete that. But it tells you how many amps for each size, and then it just adds all of that up. And so you know that for that stop, you're going to have 11 amps, so that requires 2 fuses. Now you notice here, 7 fuses is, you know, 1 fuse over. If you really did 6 amps, you would need another fuse for that last 7/10 of an amp. We would only fuse that with 6 fuses because we'll give those some headroom, especially when you're using slow blow fuses. There is some leeway. And in the chart section of the notebook, there are some pages. So if you look under section 4, and kind of page through till you find about time delay glass fuses. And these are the MDL series. It goes through and says, if you look down at MDL 6-R, it says 250 volt rating. And then it tells you, up above.
It's immediately after the PowerPoint.
Yeah,
It's after the PowerPoint.
yeah, it's after the PowerPoint. Looks like this.
Maybe either this one or the one that.
Yeah, it's just. So you notice up above, under the rated current, which we're talking about 6 amps. So at the very top of the page, it shows you that if you go to 135% of the amp rating, it'll take 60 minutes maximum to open the fuse. But if you go to 200%, it'll last for 120 seconds maximum. So, and 12 seconds minimum. If you look down below, then up to 8 amp fuses, if you go to 200%, it's going to last for 12 seconds. You're not going to hold a cord much longer than 12 seconds. So, at least we hope, perhaps. So, you know, you do have some headroom with those fuses as well. So, you know, this is an automatic calculation, but you can then apply some logic to, okay, I'm not going to go quite to that extreme. So that's a way to do it. You know, you can come up with your own spreadsheet. If anyone wants this one, I'd be happy to share it with you. But this is just kind of how we've done it in the past. Any other questions?
So how do we accomplish?
Stand up, Aaron.
Oh, I'm getting up. You know, the funny thing is Bob had mentioned all of the components that we were going to talk about today already. What we normally do to accomplish this is use these things right here. I don't know how much more I can really talk about since Bob so thoroughly described what we do.
One of the things we can point out is with this one, this has the option of having your negative bus at the bottom. You can also buy them without, which is what we usually do, and we have a separate bus bar that we buy for negative or ground bus. And one of the reasons we aren't quite so comfortable about this is you have your positive wire going right over top of your negative bus. So we kind of like to separate that out a little bit. But,
So how can we talk about that?
so as far as you know, with dealing with these systems, you're trying to protect the wire. I mean, that's kind of what this goes back to. And so, you know, providing the fusing in as many places as possible. And this is actually, I wanted to talk about slider magnets. That's something where, you know, a lot of the slider magnet manufacturers tell you you don't need to fuse because there's a fuse on the card. But that doesn't really, again, that kind of, even though that is not a chemical fuse, it is a glass fuse that will blow and you have to replace it. But it's not actually protecting the wire. But I think like Solid State Logic and their cards, they tell you should not fuse between the cage when you use those and the.
I think generally they're talking about not fusing the lead that's responsible for the spark suppression.
Mm-hmm.
You don't want that one to go away.
Mm-hmm. And that's the positive that connects the bus to the main.
But I think the thinking of the fuses there was more to protect the transistors
Mm-hmm.
from dead shorts somewhere in the other end of the flaming wire.
Right.
Then keep you out of jail.
Right. Right.
So, to talk about the slider motors a little bit more, we don't, like he was saying, we don't fuse the cards, but we fuse the slider motors. Most people might think, well, do you fuse individual slider motors? Well, we treat it like we would stop magnets, valve magnets. So we calculate what we do with the slider motors and say, okay, and by the way, the Buffalo Holy Trinity, we used, correct me if I'm wrong, it's 15 amp fuses, so we lumped together the appropriate amount of slider motors on that one fuse, so that we don't have this array of fuses beyond anything that's practical.
Because of course, if you look at the previous chart, you know, the slider magnets, the larger hoist slider magnets, those are drawing over 3 amps.
Right.
So you can't put more than one of them on a fuse because then you would be over 6 amps. So that's not a good situation to be in when you're dealing with an organ that's having 2 magnets going at the same time. So, you know, by using 18 gauge wire to run the slider magnets, you're outside of the 20 to 28 range, which it used to be, I think, what, 26 and 28. Okay, so now it's 20 to 28. So by using an 18 gauge wire, you can put that on a 15 amp fuse.
Right, and the return is not a 14 gauge, it's a 10 gauge.
Yeah.
So that it can handle all of that current.
Yep. Other questions about how you fuse?
A question, Peter, how do you physically arrange to return the ground connections for a group of slider motors? Where do you collect the maximum number of motors that you're going to have on one cable or one fuse?
We usually collect them on near the slider magnets. We have a bus bar usually at the magnets, and then this goes back to philosophy. We usually have the fuses all in one location, so you don't have to go around the organ hunting for fuses. All the fuses are on that one panel that you saw for the entire organ, which is why it looks so overwhelming. But you know, so we have a bus on the spreader strip that we have at the slider magnets.
Right. So you'll collect 2, 3, or 4 magnets together on a single wire that'll run over to the fusing location with its own fuse.
Right. We've had instances, as a matter of fact, Buffalo Holy Trinity was they had their own card. This was fusing for, and let's be clear, this was fusing for magnets, valve magnets, but they would put the card, the driver card, in the chamber, so we would run across cards mounted on walls, and if a fuse blew, we'd have to find out where this card is. So how do we solve the practicality about that? Well, eliminate out of that and just centralize everything. And the photo of there showed every fuse in the organ is located on one panel.
David Harris used to make, I don't know if he does anymore, some very nice fuse panels for 3AG fuses that had a two-color LED on it. And if the LED glowed green, the fuse was good. And if it was red, you knew it was blown.
Whoa.
So
Where's
any,
that?
David Harris from Whittier, California made these.
How many fuses did you end up putting in Buffalo?
Well, there were 21 fuse blocks for 6 amp fuses. And not all of them were full.
Yeah, no, well, most of them were. We were near capacity when we did that. There were 3 15-amp fuse blocks for the sliders, and there were 30-amp fuses for wiring,
Mm-hmm.
and then 6-amp fuses for the magnets, and that there were 3 rows of between 6 and 7 blocks each.
So can you go back to the picture of the big bus? Because I wanted to see if we protected the wire like Bob said we should have protected the wire. So the 2 things on the upper left, those are just big bus bars.
Yes,
So
1,000 amp bus bars.
So coming out of the 5 power supplies, they each came into that with what gauge wire?
4 gauge. Each one of them had, the rectifiers were fed to that by 4 gauge wire.
Okay, so then we assume that the fuses in the power supply protected that wire.
That was the original assumption, yes.
And then
What are
after
the
that,
ratings of those what are the ratings of those fuses on the 70, no, I mean the blade fuses on the power supply?
240s, I think.
40, I'm sorry, yeah, 40.
Yeah. And then those, the, out of this, the positive bus bar here, we went to these 4 fuse blocks, and those all had 30 amp fuses in them to feed the 21 fuse blocks for the rest of the organ. So these all had 30 amp fuses in them, or 6 amp fuses in them to feed the organ. And then these were the 3 for the slider magnets that had 15 amp fuses in them. So we did not have a fuse right at the power supply, but like Rick said, we kind of assumed that the fuse on the power supply would protect it, but of course you still have the issue of wire. So
come on, Bob, now you got to say something.
Actually, I do, because the fuses on the power supply are not to fuse the output. They are protection against reverse polarity. They're not gonna fuse you for an overload.
Where are they located in the power
There
supply
isn't,
circuit?
there's a dead short circuit or a limiter, but there's no fuse or protection device in the power supply.
So these 2 blade fuses that stick in
That
there.
is for reverse polarity only, because the power supply is actually, its initial design is as a battery charger. So, that's what they're there for.
So we should have had a 40 amp fuse in line with
I think we said 80 amp fuse.
80.
A
On the
75 power
75
supply.
Yeah.
Big cartridge fuse?
Yeah.
Yeah.
Well, that's why I mentioned, one of the reasons to host this thing was every time we did an organ, we'd think of something else that we didn't do last time. There's one right there. I mean, it's trying to understand fusing each wire size, and that's why I brought that up. So we went from this bus bar to 30 amp fuses because that wire size dropped down to a different
Yeah.
Right.
size, and then it went to the distribution of for the slider magnets, and then the smaller. So we tried to protect all the wire sizes when we were doing this. Obviously, we missed one little link, but
Yeah, but you know, we used to think, at least I used to think, wire sizes, you're thinking of voltage drop. You're not thinking of catastrophe.
right.
Do you have a chart or do you label what each fuse does?
Yes, we have a book that each each block is numbered, and then each leg is given a letter to tell you where it goes. And then right above each block, it tells you what fuse goes into it, so that you can't put the wrong size fuse into it.
Yeah, because there's a, you can barely see it. There's a D there, so that is a D. fuse.
That'll go to a D block. This way we don't confuse it.
And you know that always learning something new goes to the fact that this is actually the first time we fused the returns for the slider magnets. Canandaigua, there is no fuse on the slider magnets other than what's on the cards. So you know you learn and you go to the next one. So.
Because we learned, just to reiterate, that the fuses that solid state people put on there are to protect their own circuitry. That's not to
Basically, yes.
protect the wires.
Right.
So
But even the fuse on the slider motor would protect your wire if you wired just one slider motor at a time. When you bust them,
Mhm.
now you're not taking a big wire over these motors
Right.
and busting them. Now you got a different problem.
True. Right.
okay, so
Except,
E perspective.
Yeah.
now, see, except it isn't protecting the infrastructure.
Well, still, basically, on that slider motor, the wire's going to come into a terminal. If it simply right there goes through a glass fuse, it does protect the infrastructure because the current can only go through there.
But of course, on a
If
slider,
somebody were to short the
You're-
cables feeding,
You're right. If somebody leans a ladder, aluminum
Right.
ladder across that wire
Right.
and cuts it, the wire is not protected.
and that all goes back to what we're talking about tomorrow, which is protecting your wire with some kind of duct or some other way of doing it. So,
You're headed towards complying with the low voltage code,
Yeah,
which is a good thing.
That is.
and as a matter of fact, if you notice, most of the organs that we build, there's a panduit,
wire
a
duct.
wire duct,
Yes.
wire duct or something covering the wire. Even though I know the code doesn't specify it, but this is how we try to avoid any of these shorts that we're talking about. And I don't want to try to promote another NEC code, but that's how we avoid the problems. Because we've had pipe toes set on wires and things like that. And we know
Or
they-
fiber optic
Or
cables.
fiber optic cables, yeah. So we try to avoid that.
Things that look like that are things that make inspectors happy because they've seen that in other places like industrial installations.
Right.
Well, that's the kind of thing they expect to see.
As a matter of fact, tomorrow's PowerPoint is going to deal with a lot of, I don't want to take a left turn here, but tomorrow we're going to be talking about a standard that's called IPC standards, and it's industrial, and that's kind of the direction that we're trying to go with this company anyways, and AIO is now a member of it, directly now because we had to do photocopies. The whole point is to make sure that when we look at an organ, it follows a way of doing things that somebody can walk into and recognize it, that has no idea what a pipe organ is. Hence, we use the plastic ducts. Or we use what Dick Houghton does, and you watch the way his wiring follows. Everything is neat and as a matter of fact, absolutely gorgeous. The whole point is to make sure everything cannot raise a question. If you start raising a question with sloppy wiring, then you're going to raise the question. Then the questions, red flags are going to come up with your inspectors. So our whole point here is to make sure everything is neat. and for my end anyways, because that's what I deal directly with. Peter will deal with a lot of the calculations and hand it off to me, and then we'll talk about it. I don't know how much else I can talk about right now, unless I end up going into my own PowerPoint. That's tomorrow.
Okay, and then one other thing, one reason we use Panduit is because the covers come off and the wires come out. Like when you're wiring an organ, Dick, you're usually doing it on site, right?
Yeah, and the problem I have is with my colleague Vladimir, who sees the Panduits as a means of hiding sins,
Exactly.
Well,
which he won't do. So every cable is neatly laced or tied inside. The Panduit might as well not be there as far as the is concerned.
and ironically, if you open that Panduit and you look at the commons in there, that's exactly what's in there. But it helps to cover that so that it's protected. And in this instance, it's such a rare instance that we wind up doing an organ like this. We don't want anything happening to it.
And in this particular case, that did not get unwired to move the organ, but we use Panduit elsewhere in the organ because we set it up here, we test it, and we have to unwire everything, and I don't want to unlace, 100, it would just be really time consuming. So the Panduit is a way to make that still look neat and protect it and be able to take the organ apart.
So, what else? The other. Oh, there was a better picture of the bus bars. And so this kind of goes back to that point. You see, there's the letter A, B, and C. So that we know we have fed off of this fuse block A which fuse block is being fed by it. So we're keeping track of which fuse block is being fed from up here, and then also down here where those fuses are coming from. This was in the shop, so you can't see the breaker panel that feeds the power supplies is actually right at the bottom of this panel. They installed that at the church. It's unusual because the breaker panel is actually fed by a contactor. So there's only power on the panel when the organ switches on. And so in that panel are the 5 circuits for those power supplies, a circuit for another power supply that's in a room behind where the walker system is. And then there's two circuits for the console power supplies. So those are fed back underneath the floor because the console is on the other side of the chancel from this chamber. So all of that is fed off of that one breaker panel. So you only have one place to go, but of course when it was tripping 3 circuit breakers, we're going, why is it tripping 3 circuit breakers? And it didn't happen every time, but that's where the high magnetic breakers come in, which I think you're going to talk more about those tomorrow.
I have a question on the breaker panels, because this question came up. How really important is to balance each leg within the
It's very important.
okay, because that was
Because,
another,
again, that helps deal with your inrush load. If you've got everything loaded on one side and not the other, you really don't have the capacity of panel shared. So
because that, from what I understand, was another question. Are the breakers popping because of that?
it may have been a minor contributor depending upon how low the voltage is going, a startup, but more than likely it's the inrush problem.
Has anyone else experienced breakers popping like that?
Yes, we did, it's funny, we have it on our organ at Virginia Theological Seminary. We just run, it's three breakers, big part of it, it's his fault.
He, this unlicensed
But the,
organ builder guy, did
That's
all the
right.
high voltage stuff just beautifully.
but the, when you turn the organ on, it would occasionally trip a breaker.
Mm-hmm.
And I'm sure the high mag breakers would fix it. I fixed it by playing around with, there's a 3-phase panel,
Mm-hmm.
playing around with what leg I was on, pulling off for the rectifiers, and fixed it by better balancing the loads on the legs of the panel.
Because you're not going as low,
Yeah,
it started,
yeah. That fixed it by
you got lucky.
jumping around on the panel. And then-
You had a three-phase panel.
Yeah, I had a three-phase
Oh.
panel.
Yeah,
So
we had a
Two-phase.
220,
This is- yeah, this is only
so we didn't have that much
We
to
had a
play.
dedicated, it was a panel they put in just, it was a new building for the organ. So we-
Okay.
It was one breaker, and I started changing stuff around. I finally got the right combination of power supplies and breakers together where it could.
Yeah.
And we
Good.
haven't had a problem in a year and a half, but the
But-
high mag breakers have been an easier solution than the.
Yeah. Well, and, you know, the frustrating thing is, of course, it doesn't happen every time, and so
Right.
you don't
I know
even,
it'd be fine for a week and then it would trip.
Right.
and you wouldn't always know that it happened.
Well,
That was the other thing.
Well, we're only running stop action,
Right.
and it would lose one of the pair of rectifiers running our stop action, and it would run fine with one power supply
Mm-hmm.
Until.
Until you hit a big.
But as Dick said, those power supplies are rated in watts.
Mm-hmm.
If your line voltage is low, when they decide to suck, they're gonna be sucking more amps
Right.
to fill up their reservoir.
Mm-hmm.
So if the line voltage is high, your inrush current will be lower to fill
Yeah.
out the same reservoir.
Right. And here we do have, when we check the church voltage, it's 122, so it's not even like it's 110, but it is 122, so it's,
Well, also it depends, when you draw an inrush, did you look at the transient, at what the voltage really did?
as best we could.
Yeah.
Yeah,
As best you can, yeah.
yeah. And it did go down, but not much.
They've got a fast meter.
Yeah.
Yeah.
Any other comments on that? Phil, you said you had that same
We've run
experience?
into it a number of times over the years. We've run into asphalt, we run into the switching power supplies
Mm-hmm.
as well. Because the meter is immune to it.
Right.
Usually we find that getting them to size up the breaker, none of the electricians have ever mentioned these magnetic breaker systems. This was new to me today, so.
Yeah, it was new to us like a week ago.
Yeah, right after I got a phone call and dug a book out from 15 years ago that said, how do I deal?
Electricians will probably become more and more familiar with this as switch mode power supplies invade various pieces of
Well, the
equipment.
example that's given for these breakers specifically, like if you actually do a hunt, after I said, okay, then I immediately went to Amazon to say, how much are these suckers? And one of the examples that's given is for commercial lighting, commercial lighting applications. You flip the contactor and the whole plant lights up. And the inrush is, and so it is not old news. It's new news to us as we start using larger and larger power supplies on more complex instruments.
Mm-hmm.
I mean, I don't think anybody's had a 55 on a 15 trip, and most circuits are 20 million.
Right.
So.
How about the issue we had with the walker system?
Well, and part of the issue with this was the first symptom was the circuit breaker that tripped the most was the one running the 30 amp power supply for the walker system in the back. And so that was kind of unusual because obviously that's not a huge draw, but it was the last circuit breaker in the line, so we're just thinking maybe the voltage just got so low by that point. That was kind of the only real thing we could do to explain that.
There is such a thing as a weak breaker.
Right.
Yeah, and that's when we actually took.
I mean,
We swapped them.
We actually I took the breaker out and put it somewhere else where we knew there wasn't going to be.
your electrician took the
Oh,
breaker out.
Yes.
Your electrician took the breaker out.
Oh, yeah.
Scratch that. Is it being recorded?
Oh, it's Rick on the record.
Stricken over that.
When were you going to talk about that?
Tomorrow.
Okay.
Okay, good.
So is this a different issue than we were talking earlier about power supplies? We had an instrument in Florida that was running on some fairly high voltage because of high pressure. We had, electric pull downs on the pallets, but it kept tripping and they kept isolating circuits with the in-house electricians. And finally what we found, the thing that worked, and now I carry in my toolbox is, I'm pronouncing this right, thermistors,
Yeah.
that I put thermistors in all of the rectifiers, which slowed it down on the, when it fired up, and we haven't had a moment.
Which rectifiers were you using?
That name was Astron.
Oh,
Yes,
Astron,
as
yeah.
a matter of
I
fact.
put one in a switching power supply once, and the supply failed the next year, not the next day. And I didn't know if that was a bad thing or not. Maybe it doesn't like to have a slow start.
I believe not. They wanna come up,
Mm-hmm.
they are looking for instant gratification.
Oh, I can relate to that.
That's an interesting question, because we were testing, that Walker supply, and we were using different, rectifiers to figure out what was going on, because some of the IOTA rectifiers we've had were faulty, and we were breaking breakers constantly.
So
So
we
would-
blamed it on the IOTA supply.
So we tried IOTA, and then we tried IntelliPower, and then we tried an Astron. And when I hooked the Astron up, it literally jumped off the floor.
I think it might actually be this one.
Yeah, it jumped off the floor, and there was a loud pop and a big blue spark when it happened.
Whoa.
So we're still struggling with why something like that would have happened. There were
When all is connected to that circuit, are all the amps connected to that circuit?
No,
no.
the amps are on a separate circuit.
All it was driving is the 30 amp
The 30 amp.
rectifier.
Have you just bothered, now that you have the meter, meter the peak startup on that DC circuit feeding Walker? You can, with the amp over essentially, you can set that to peak and take a reading.
Okay.
Now,
You may have something going on with the Walker.
So do you know what sparked in here?
No.
Or is it that?
No,
I
actually,
don't know.
That was.
I can tell you where it
Yeah.
happened. So here's the switch, and
Yeah.
I saw the darn thing just lifted right off the ground, and the spark was right in here, right underneath.
You had the
where the
cover off?
No, no. I never start the unit up with the cover off. But wherever it was right directly beyond the switch.
Oh.
Never seen that happen before, ever.
You never know quite when to make the video. do you?
Yeah. Did it have that smell, that fried electronic
Of
smell?
course, no, that didn't.
Because that doesn't.
Okay.
No.
This must have come from somewhere else.
But now, Aaron, you say it did not after it popped.
It did not. I know what that smells like.
So then it didn't hurt the unit. It was just something defective inside of it. I don't know.
I don't know. That was, and the reason I brought it up is because maybe somebody's experienced this before.
Do you still use Astrons?
Not really, unless I, have taken them in trade and changed something.
We've had so many problems with them, we just don't use them anymore.
Oddly enough, it's the 24-volt ones that drop like flies.
Oh,
Steve Deek took a bunch of their 24-volt dead Astrons to the Astron company in California, and said, why are these failing? And their engineerish kind of guy there, plant foreman, said, well, he didn't really know, but maybe the parts were under greater strain than on the 14-volt ones.
Hmm.
So they don't know. I don't know.
The upside to the IOTA supplies, 2-year warranty, it's a UL product, even though it's made offshore, they own the plant. Okay, they own the plant in China, and they have an engineering team that if you need help, you can pick up the phone and get somebody on the end of the phone.
What do they say in terms of changing the voltage of the unit?
I've had that discussion with the plant. Their standard comment was, that's not how we designed it, but, not squawk when I said I was dialing them up to the max, which is almost 16.
Yeah.
And they said, if the regulator will go there, I guess it's okay.
Yeah, I've taken a 75 amp one up to
Right.
a little over 17.
Yeah.
And
Yeah.
I figure it's smart enough to look after itself.
Yeah, they've been,
That's fair.
they've been, really good to do business. So just, OSI sells them, SSOS sells them, Amazon sells them.
What does Peterson sell now? Who makes
And
those?
telepower, and just an aside on these power supplies, there's another, we'll regress to the worst. Power Max. Runaway, runaway, runaway. They do really, really bad things on shutdown. And I've actually talked, the kid who is importing them is an ex-IOTA sales engineer, who somehow got somebody in China to build him something. But if you put one of theirs on a scope and look at it at power down, it does 4 to 6 big spikes.
Well, even IOTAs will do that.
One or two, not as big. I mean, these
Yeah.
are.
Well, I've
these-
had cases where I've used the IOTA in the console to run a little ice cube relay
Yeah, and
to
it
start to
does,
kind of like
yeah,
that.
right.
So it's off to the Radio Shack if you can find them anymore.
Yeah,
And I just got a 6-volt Zener diode
yeah.
and put it in there. So basically, the ice cube relay doesn't see any voltage
Direct.
from the IOTA
Yeah.
unless it's above 6 volts.
Yeah.
So it goes down from 6 and
Yeah.
at the end, it works, but it's a nuisance.
Yeah, but the IntelliPower is better than the Power Max, but worse than these guys. So,
What have you seen with the IntelliPower?
was that
What have you seen with the IntelliPower?
spikes, big spikes? And I'll tell you, when the OSI slow motor was being developed, the engineer there, we were looking at all the possibilities of how to break a slow motor and use all different power supplies. And the IntelliPower was one that just gave us fits, and finally, he put a scope on it, he says, the thing shuts down so dirty you can't stand it. I mean, these aren't super clean. You gotta understand, all these power supplies are made as battery chargers and power supplies for RVs, boats, and so on. So they've got a battery or a bank of batteries hung on them that acts as this nice, wonderful filter that they don't care when you turn it off what happens. So,
Where does,
yeah.
where does the Zener diode go?
You have the IOTA power supply there.
Yeah.
Going to bus bar. And when it switches down, the bus bar doesn't just cut to 0, it goes down, up and down a little bit.
Yeah,
So you put a Zener diode, let's say on the positive rail there,
okay,
and take it to an ice cube relay in the blower room, and with a negative return too. So the Zener diode will conduct current to the ice cube relay only when the voltage goes above 6 volts, or whatever Zener diode you've chosen.
okay.
So it's mostly for a startup kind of.
It's for
relay.
it's for shutdown.
It's for shutdown.
The ice cube won't turn on until you got about 3 or 4 volts across it, plus 6. Now you're at 8 or 9. So
Yeah.
as soon as that power supply starts down the slope,
Mm-hmm.
it's going to drop out. Hopefully before you get the rest of the trees on the ski slope down.
Could you go back to that swell shade linkage? That looked amazing.
There are 3 OSI swell motors on each division. The 2, you're looking down the choir shades at the moment. The 2 choir shades open like this, so they're going in opposite directions. So that's what the linkage is. And then you kind of see the side shades here.
You guys made some nice welded arms for the OSI engines, didn't you?
Mm-hmm.
You might tell folks about that.
Actually, yeah. My son did that.
Oh,
He just finished his certificate program at Ohio Technical College. And Rick had the arms designed so that the Yeah, we have, this is kind of real diversion on what we're doing, but that's okay, I'd like to talk about it. The collar that goes onto the motor, actually had a ring machined into it so that it fit inside of the arm itself, but it didn't fit in the hole that was opened up into the arm. The arm hole was wider, but it had 4 teeth to hold the arm to the collar, and then my son would fill in that space, that gap, with weld and then grind it down. And then they were powder coated. The dilemma that we were having was that ring was press fitted into the original arm, and it would turn, so that arm would just wobble back and forth. So we solved that problem by having everything welded, and to the point where you wouldn't even know it was welded.
So Oregon Supply, we had a bunch made for us and them. They actually offer, if you ask for it, they'll give you the heavy duty arm.
For a price?
There's an upcharge, but I don't think it's much.
So
It's beautiful.
And so it's just, we used a bigger collar. The hole that was drilled was sloppy, so it's a machined hole, and the arm is thicker metal, so it doesn't flop. And we sized all the slots for 3/8. What do you call those ball joints?
Yeah, spring fix linkages.
Spring fix linkages.
So,
And if you buy those things, you can point the end at, you can see the blue material. Is that blue?
yes,
Okay. I just
purplish
can't see it.
blue. Indigo.
So the normal material is white or something, and one of our guys working here found out that this blue material is way tighter tolerance and there's no play in it.
It's the noise.
Yeah. So if you buy those things, you should look for that.
And these are not expensive. They're like $3 or $4 a piece.
Wow.
They're pretty cheap. So,
Say that again, please.
spring fix linkages.
That's the company.
That's the company.
Okay, that's the name of the company?
Yep.
Thank you.
Springfixusa.com. If you just look for springfix.com, you'll get somewhere else. It's like springfix-usa.com.
Thank you.
Mm-hmm.
We were talking, some of us a little earlier, about using the OSI engine, utilizing gray code to get up to 60 stages of them. A lot of people don't realize that. It is covered in the OSI installation manual, but usually, we all just read 16 wires, hook them up here, 8 wires, hook them up there. But it's an amazingly cleverly designed engine. And I think when Fred was developing it at OSI, I was in the room, and he had like a clock face with an arm on it that was going around, and he was running this thing off a Laukov supplied gray code. It looked like potentiometer. It was really putting out gray code, and he was very justly proud of that. And it's really very smooth if you use, well, like I said earlier, a pot or the string pot or anything like that, and run it through an A to D converter. It makes a beautiful job of it.
Mm-hmm.
You do know they've improved it, because most of the market doesn't know. You need to get their sales going. The SOPD, if you order a 251-1, the open on power down is built into it now.
Is it still a bank of capacitors?
Yeah, it's still the same card. It is just
Inside.
wiring and the unit itself is
How
incorporated
long do
into the
you-
same housing.
Evil question, how long do you expect those capacitors will work before they dry out?
Till about a week or two after
The
I'm gone
warranty.
from OSI. I wouldn't have an educated
Yeah.
answer for that.
You've got motors out there with them for 8 years now.
Yeah, but 8 years
Yeah,
in the
no.
life of an organ.
The life of capacitors is rated in, electrolytics is rated in power on hours.
Mm-hmm.
So that organ's not powered on very, and they're frequently rated 10,000 hours of power on hours. How many hours is it over power on? Not very big. So.
Manuel in here?
Depends on
No,
what-
he's downstairs.
I mean, we've used, I don't know if you've used them, but we've used hoists before, you know, they, for $2,500 you can buy a hoist, or a Laukuf has them now too, linear motors that are supposed to be infinite, and they're probably more than that. That's what they cost 10 years ago. But you know, we used them, and Manuel had them at Disney,
Yeah.
and he was having trouble. I mean, getting something from Germany, you know, tech support and all that. But he switched all those out to Oregon Supply, and he's really happy with them.
Yeah, he did. And to back up a stage there, this is the Walt Disney Concert Hall. The attached console and the tracker organ. On either side, right next to the console, are the shades for the Positive division. And when the organ was built, they used hoist motors, which are this sort of action, like the Laukuf one, but they didn't offer a logarithmic option. It was linear. And so you just touch the pedal and boom, the shades are open, and it's like an assault to your ears. So some years ago, I changed the hoist ones to Laukuf engines that did offer the linear thing, which is marvelous, because that's the way we hear. And the OSI engine has that switch, so that if your linkages don't logarithmify the motion, then you can select it on the engine.
Does everyone hate the Peterson motor?
I didn't want to say that out loud.
I get lost in that tree of adjustments.
It requires AC power.
Yeah.
It requires DC power. It requires a data cable between the head and the machine. It weighs like 2 cinder blocks. I mean, when you're standing on top of a swell box.
I am standing on top of the swell box. I put them in.
That's right. So, I mean, they live forever. I mean, I've got one at my own church that after 4 hours of swearing at the thing and so on, and I got to finally adjust it. I'll be honest, my gripe with them always was, and not because I had anything to do with the black box that goes from here anymore, but it didn't come programmed even remotely like you would use it. Okay? You know, take it out of the box and at least have a default that is a reasonably maybe 75% of the time operating mode as far as staging and so on. Every time you took it out of the box, you took a new one out, you had to spend whatever amount of time dialing the bloody thing in.
I'll admit that.
Okay, as opposed to the first order that was given to Fred, when Fred designed the OSI one, was, yes, linear and logarithmic and plug and play. Okay? And actually there was a programmer developed that, because a few people said, oh, we want to be able to set it up ourselves. Okay, fine, so Fred developed a programmer that plugged into the maintenance board, so you could go and, I think we sold tools. Okay, had they been sold? Yeah, see,
I didn't even know they had one.
No,
Yeah,
I didn't either.
I think the biggest thing is you can take an OSI swell motor out of the box and go replace an air motor with it and walk away, as an example. Or you can take it out of the box and hang it on the wall, and if you follow the simple basic rule that, what's the simple basic rule? The arm has to be in line with the arm, okay? Not 3 degrees, not 5 degrees, put it in line, works every time. And being DC powered brings a whole level of less complexity. If I don't have AC power and I'm replacing something, now what do I do? Now I gotta get AC powered. So, and I think it's a thing of hate, it's just, it's also, all, you know, I mean, I got nothing to win anymore, but I just tell you this, I mean, it's the basic Peterson swell motor, 25-year-old design, goes back to the old 100. So,
Well, Scott, in spite of all that stuff, we used them, and the only reason we switched to Laukuf until Oregon Supply came out was because we could never get them to work smoothly. I mean, it was always bouncing.
Even with all those adjustments.
Yeah.
I used to get along okay with the old ones that had 8 pots, and you set each stage, and that was a no-brainer. The new Laukuf engine has a new controller designed by that guy with the ponytail who's so smart. And it actually has an LCD display inside it, and you can see the curve. It's not just log or linear. You can tweak the curve, and what you see is what you get. And they've dealt very cleverly with the open and closed limits. You manually close the shades and push the learn button, open them for how far you want them to open, push the learn button, and it does it. So it's very interesting to see the development of that machine pass through the brain of someone who's not from our industry. It's like we were talking about their new slider motor that doesn't have strength controls. You know, we obsess about, oh, should the controls be on top of the solenoid? No, we can't get them because the 16-foot Borden lives there. Oh, we'll put them in a box. Well, this guy looks and said, well, excuse me, but why do you need strength controls? Can't we make the solenoid control smart enough to know what it's doing?
Measure the load.
Yeah. So it's kind of refreshing to see, you know, people thinking out of our little box.
Yeah. Do you know offhand what the locomotive motors cost now?
They don't cost, I bought one.
Did you?
They don't cost any more than the ones that you bought before with the control card.
Oh, okay.
They priced them to basically match the price of what you were paying before. They may be €20 more or something.
Yeah, what they want to do is actually reduce their range of solenoids to that one
Yeah,
thing.
to one thing.
It'll do 12 volts, 24 volts. It'll, you know, move the earth if it has to. You don't need a big one and a small one. So
Okay.
there's a, you know, the manufacturing self-interest there.
Yeah, they don't. They're selling them cheaper right now. Actually,
They're €200.
they're €200 right now, which is even less than what you would have paid with them before.
But you save an
The normal
awful
price
lot
is
of
a little-
an awful lot of wiring.
Part of
Solid
all
state
this-
control comes with it.
Yep.
It's right on
Down the
top.
top, okay.
It has optical sensors that look down at how the shaft moves, and it tweaks the control automatically to make it move promptly but quietly. And the demo they had at the last couple AIO conventions consisted of a slider clamped between two wooden blocks with thumb screws on, and you could vary the force on the slider. And I'm not kidding. You could tighten those down so you really couldn't move the slider, and it could. I suggested for the last convention they put an amp meter on it so you could see how it was doing that. And it just ramps up the power as it needs to. But the cards do have a 6 amp fuse on them, so it's sort of a nod toward our code.
Part of the issue with all this, and that was part of the discussion in Erie 10 years ago when the slow motor was starting to be developed, was, first of all, what is the value of time? And like this slider motor. You know, so I save $50, but I spend 200 in time.
Yeah.
And I think that's one of the questions, like the Peterson. There's nothing hating the Peterson. It is a good, solid product. I mean, you get it adjusted right, and it doesn't get hit by lightning, it'll live forever. Matter of fact, the motor in that thing is ridiculously overkill. But so many organ builders don't value their time. I mean, I hate to say that, but it is, I'd rather tinker with this thing to death than move on to the next job and make more money. And that's slider motors, all this technology stuff can either be your friend or a giant invisible money hole.
And even if you don't go on to make more money, you might go on to have a life.
Yeah, that's right.
Or something. So.
Is there anything you want to talk about in specific? Because I noticed a couple of things. I just noticed a couple of things that triggered some memories on wiring and fusing. We have to deal with large bundles, and some people will use a stiffer wire just because it's easier to get. What we wind up using is what we call MTW quality wire. It's a machine tool weight wire, so that the strands inside it are lighter weight, but there are more strands in it, so that you don't have really harsh, really, how do I want to describe it? Say for-
Spring steel.
Thank you, thank you. An issue with running your cables neatly, because that's another issue that if you were to use a regular weight, I forget what it's called.
Well, Home Depot.
Yeah,
PHA.
Home Depot, if you went to Home Depot and got your
PHA,
supplies, yeah,
Right.
if you got your supplies at Home Depot, it could do your job, but it's not going to be neat, and there's no way on earth that you're going to be able to fit it in Panduit or on your boards neatly. So we use a product that not only is the wire flexible, but the casing is flexible too. So that's something that you might want to consider when you.
Is that manufacturer called out in the handout?
It should be. I think everything is there. I can't pinpoint all of it right at this point, but most everything that we purchase is on these.
What was that acronym again that you had said?
MTW, it's
MTW.
machine tool weight
Machine
wire.
tool wire.
Machine tool
You've
wire.
got flathead to run your cables, you don't, doesn't matter what.
Well,
color.
you know, it doesn't matter for him. We go to the Home Depot and he gets that stuff.
I know,
And
you-
he does it beautifully, and I say, I can't do that. I don't have the patience or maybe even the strength anymore. But he says, I will win. And, you know, it's you know, to my will. The same way he treats his lady friends.
I have samples of that type of wire with me, we'll look at tomorrow. And another source for that type of wire is the local marine store.
Yeah, I think the last time we did get it from like marine grade or something like that, and it was even finer
Yes.
wires in there, and so it was actually very flexible.
It's very nice to work with.
Yeah,
There's,
even the 4-gauge wires that we ran from the power supplies were still relatively flexible.
There's a supplier in Las Vegas that Steve Deek put me onto that does that sort of thing. It may not be as fine as the marine grade, but it's twice as good as that, or only half as bad as that.
Yep. And the
I don't have anything else I can add at this point.
yeah, as far as point of today is to talk about fusing and just how to comply with the code, and hopefully this is somewhat helpful with that.
I had a discussion with the German invented dude with the ponytail about fusing, because I tried to explain our NEC, and this was the previous 650, which was just concerned about 6-amp fuses, and he said, but you don't protect the wire. And he was saying exactly the same thing we were hearing today. If you went into a German organ built in the 30s, 40s, or 50s, you typically find this thing that looked like a wardrobe closet in the organ, big panels, and it's all scarred up at the bottom. And if you opened it up, there's one fuse for each and every magnet in the organ. And even worse than that, there are those fuses that we used to have in VWs. Do you remember them? Sort of the pointed end with the foil. So the organist knew if something didn't work, the first thing they did is go up and kick the cabinet. So they've come a long way from, it's interesting, they've come from the overkill, stupid position to something that's, modern and technologically correct. And we're coming from our own dark ages with no fuses.
Yeah, I mean, like Bob said, there's so many organs that we take care of that don't have any fusing on them, and so it's all of a sudden learning more and more about it. What do you do with all these organs you take care of?
Write a note. We advise that this is not to code, and we've just learned this, and
Yeah.
we'd like to let you know that this something should be done about it, or
Yeah.
else.
And we'll do it for you for a mere.
Yeah.
That's where the stickiness comes.
Well, and you guys have you made a summary of, in the section 4 of the notebook where a lot of these charts are that we put in. I think the last one is kind of a resource summary of where we buy a lot of our
Yes.
tools and fuses, and it's probably more stuff you're going to talk about tomorrow.
Yeah, most of the rest of it we'll talk about tomorrow, but it has the 6 circuit fuse block covers that we talked about, as well as the mini bus bar that we also use from Blue Sea, the fuses, and then you can also get the automotive fuse block from Blue Sea's. And you'll see that in the Canandaigua console tonight. We used the automotive fuses in the console there. And there should be a disclaimer at the bottom of the automotive fuses section. It says the code says 6 amp fuses are smaller and must be used for 26 gauge wire. That's the current version of the code that goes out of date on December 31st. So it says automotive blade fuses come in 5 amps and 7.5 amps. 7.5 amp fuses are to be used. 24 gauge wire will need to be used in a good argument provided for the code enforcement officer. There is no more good argument. So this was a little out of date, but it's 6 amps and that's it. So that's all you can do.
You all set?
I think we're done.